Chapter 1, Section 2. Oh, don't these look exciting?
Oh, yeah.
Formulas from geometry. Now, we're not about memorizing these formulas today, for better or for worse. Ever, you should already have them memorized. But what we're about today is manipulating formulas. We need to be able to take all sorts of formulas, rearrange them as needed to solve or simplify for something. So you probably know several of these. Maybe you have never even seen some of these. I don't know if you have ever seen the equation for a frustum. Maybe never even run across that word. You take a cone and chop it off so it's flat on top, and it's called a frustum of a cone. But what we're going to be working on is rearranging to solve for a specified variable. So here they happen to give us the perimeter formula for a rectangle, and they say solve this thing for L. So we're just wanting to practice isolating L. What would I get rid of first? Did I hear it? I want to get rid of this term. If I'm trying to solve for L, I want to get rid of any other terms that are being added or subtracted. So I'm going to subtract 2w. 2L would equal P minus 2W. Subtract my 2W. Then I would divide by 2. And my L would be isolated. P minus 2W divided by 2. That's all they were interested in here. Can you rearrange that one? Let's try this one. Now this one, we are supposed to isolate the H. Now you notice that H is both here and here. It's inside the parentheses in two different places. I'm going to have to first distribute that 2. Well, I guess I wouldn't have to distribute the 2 first. Is there another way to get rid of that 2? You could say multiply by the reciprocal. Maybe even more simply put, I could just say divide by 2. I'm going to divide by 2 and get rid of it here. So I'd have S divided by 2 equals, and now I don't need the parentheses anymore, WH plus LW plus HL. So solving for H means isolate the terms that have H in it. Leave them on one side. So how do I get rid of the LW term? Subtract it. So my S over 2, S divided by 2, I would subtract L times W. And that equals WH plus HL. My H in two different terms now needs factored out. So it's common in only the terms that are left. I factored out, leaving me W plus L. Now, I made an unfortunate decision when I decided I was going to divide by 2 first. It's not wrong, but now I have got myself in a situation where, how do I get rid of this W plus L? I divide by it. Now I have to divide both of these things by that. So what does it look like if I have a fraction and then I divide it by something? Anybody know? Well, you could say it turns into a complex fraction. Let me start with that idea and see how we can actually make a simpler thing. If I have A over B, and then I am dividing this by X, let's see what happens if I treat it like a complex fraction, which is correct. I'm going to make that X over 1. Instead of dividing, I'm going to multiply by the reciprocal, 1 over X, and I end up with A over BX. Do you notice what happened when I divided by X, where it ended up? Simply in the denominator is where it ended up. So I'm going to use that understanding so that when I take S over 2 and divide it by W plus L, it just ends up in the denominator, just like that. Minus LW divided by W plus L equals my H. Now I'm going to put these together so that I don't have two separate fractions here. What's the common denominator of these two? What is it? 2W plus L. I have a 2 and I have a W plus L. Because in this denominator there's a 2 and a w plus l. So I need one of every factor. So this one I need a 2 and the w plus l, which means this has to multiply by a 2 on top. I'm going to write my h first. H equals, now I have one fraction, 2 times w plus l is in the denominator, and in the numerator, I have s minus 2lw. There is a nice simplified solution for h. Johnny?
I mean, what they did in the books in way simple. They started with the distribution.
I could start by distributing the 2. So let's follow up on that question. Is there one way that I have to start a problem? No, and we don't know which one is necessarily going to be the fastest way always. So starting by distributing the 2 is perfectly valid. Starting by dividing by the 2 is perfectly valid. Did we end up with the same answer? We did. So as long as you do your algebra right, you're going to be good. But you don't always have to start the same way. You just need to use a true algebra property, a correct step, and you'll be good. But sometimes, yeah, you might be the easy way or you might be the long way sometimes. Okay, application problems. This is going to be a large part of what we are doing. They're going to give us some, and I hate to use the word problem because people kind of don't like those words, but this is what we're doing. We're going to be given an application. We need to come up with an equation so that we can solve it. So a big part of doing algebra is being able to do this process. Read the problem carefully. You can't just skim over it. You've got to make sure you look at all the details. Maybe you need to read it several times. When appropriate, draw a sketch. Draw out a diagram. Label it. Sometimes that is very helpful. Figure out the unknown quantities. That is where we use variables. So why do we have letters in algebra? That's the reason. We have unknown quantities in problems. So we have to give them a letter because we don't know the number yet. And then, hopefully, you can write an equation from what the information you have found. And then you want to try to solve that equation. So let's try it out right down here. One of the best known paintings is the Mona Lisa by Leonardo da Vinci. It is displayed in the Louvre in Paris. The length or height of this rectangular shaped painting is 24 centimeters more than its width. So here I have the Mona Lisa. I will be famous someday. There we go. I have the Mona Lisa. Well, she does have shoulders. All right, there's the Mona Lisa. The length or height, 24 centimeters more than its width. Now I need a variable somewhere. Where do you think would be the best place to put a variable in my diagram or in this sentence?
You mean 24 plus a variable?
Is it 24 plus a variable? Is that a good place? Yes, it is. I don't know the width, but I do know the height is 24 more than whatever the width is. So let's just call the width W. That means the height is 24 plus W, because they described what the height was like of width. The perimeter of the painting is 260 centimeters. How do you get perimeter? There's a formula. You can say add all the sides, that is true. There's a formula for a rectangle. Twice the width plus twice the length, if you will. Twice the width plus twice the length. And they tell me that the perimeter is 260. So I can say 260 must equal twice the width. Now I don't know the width, so that's going to stay my variable. Plus twice the length, or the height. Well, I do know something for that. It's 24 plus W. 24 plus W. There we have an equation with only one variable, so we should be able to solve this thing. How do I start it? Distribute that too. 260 equals 2W plus 48 plus 2W. Now what? I'm going to combine like terms. I'm going to get my W's together, making 4W. Next, going to subtract 48. What does that give me? 212? Divide by 4. Wonder what the unit was on this. Did they tell us? Centimeters. 53 centimeters must be the width. Find the width and the length of the painting. All right, well, the width is 53, and the length is, what's 24 plus 53? How much? 77. The length must be 77 centimeters. All right, that wasn't so bad. Little reminder about geometry and triangles. Similar triangles. If two triangles are similar, it means their corresponding angles are congruent. So angle A is congruent to angle D. So if two triangles are similar, the corresponding angles are congruent. And the corresponding sides are proportional. If I go A over B, it is the same proportion as D over E. Same order. So the corresponding part. So just a little reminder about our previous favorite class before college algebra, which was geometry. A person is 6 feet tall, and they're in the shadow of a building that happens to be 4 feet tall. They're walking directly away from that building. When the person is 30 feet from the building, the tip of the person's shadow is at the same point as the tip of the shadow of the building. Well, I'm going to stop right there. I think I've got a pretty good idea of my picture I need to draw. I have a building. What do I know about my building? It's 40 feet tall, and my building looks exactly like that because there's no reason to clutter the picture with unnecessary things. There's a 6-foot person. They're walking away from the building. So we need a place for them to walk on. So they're going to walk on this. In fact, that's going to be the shadow of this building. And they're 30 feet away eventually, and their shadow and the building shadow is exactly ending in the same spot. So here's my 6-foot tall person, obviously not the scale. So if I think of the sun shining, there we go. They both are casting a shadow. The person is, and the building is, and here's the shadow, and they both end in the same place. The person was 30 feet away. Okay, so this must be 30 between there and there. I think we've gotten all the information they've said so far. How much farther must the person walk to be just out of the shadow of the building? Well, that's what I don't know. How much farther do I have to walk? Well, I need to walk this far. There's my variable, x. What I don't know becomes the variable. They say round to the nearest tenth of a foot. Well, I appear to have two triangles. I have a big triangle caused by the building and its shadow, and a small triangle by the person and their shadow. They both share this angle right there. So that's the same angle. They both share this angle, that's the same, and we all remember something called the angle-angle similarity, right, from geometry. These are similar triangles. Because they are similar triangles, I should be able to write a proportion like they were talking about right over here. So let's see if we can write a proportion. 40 corresponds to what? 6. 40 corresponds to 6. That must be the same thing as, tell me another side of the big triangle, because the 40 comes from the big triangle. 30 plus x. That would be this whole length. 30 plus x. 30 plus x. That would be the big triangle, and that corresponds to x, this side in the little triangle. So here's a proportion taking corresponding sides. 40 goes with 6. The shadow of the building, 30 plus x, goes with the shadow of the person, x. Now you may recall that proportions cross products equal. If I take 40 times x, it has to equal 6 times 30 plus x. Let's distribute. 40x equals 1, how much? Plus 6x. So let's subtract 6x. I'll let you divide by 34. to the nearest tenth of a foot? Any answers? 5.3? Yes, no? Anybody else? 5.3 feet. Now, double check to make sure that this is what they were asking for. It's the variable. They were asking for how much farther do they walk? Yeah, that's what we just discovered. They have a picture, but theirs isn't near as pretty as mine. All right. Business application. It costs a tennis shoe manufacturer $26.55 to produce a pair of tennis shoes. They sell them for $49.95. How many pairs of tennis shoes must the manufacturer sell to make a profit of $14,274? Well, we need to understand, where does a profit come from? We have expenses, and we have income, or revenue, it is called. So if I take the revenue, what do I mean when I say revenue? So you're in government, maybe you're all in government. What's revenue? Maybe I'm talking about revenue in government, but you should know the answer. What's revenue? Revenue is the money that comes in from your business. That's revenue. Nothing to do with expenses. Just whatever you do for your business, the money that people pay you, that's called revenue. But unfortunately, you will have expenses. So you're going to have to subtract your expenses from that. So in general, profit will always equal revenue minus expenses. So let's see if we can put it up here. Revenue. How do we get money? $49.95. Probably need something more than just the number $49.95. X. What does X stand for? Number of shoes I'm selling. X is the number of shoes. So there's our revenue. We get $49.95 times every X shoe we sell, minus our expenses. $26.55 X, because every time we produce a shoe, it costs us this much. And we want to make a profit of $14,274. $14,274. Oh, not so bad. Those are like terms. Can you put them together for me?
23.
283.4?
No. 2340. I'm sorry, my mom went.
2,340?
$23.
Boy, the teacher's awfully dumb. $23.40 times X. Divide by 2340. 610?
Yeah.
Did it come out exactly 610?
Yeah.
What would you do if you had a decimal?
Lowest. You can't have like half a shoe.
You can't have half a shoe, so you'd have to round down to be the way we do it. You'd have to sell 610 shoes. Sure enough, you'd have to sell 610 shoes. Investment problem. We are going to run across in this lesson several problems that fit the same type. I'm going to refer to them as mixture problems. We are mixing things that have different values together. This one is, we are going to invest a total of $6,000, but part of it is going to be in a 5% simple interest account, and the remaining is going to be an 8.5% simple interest account. Together, the investments end up earning us $370. They want to know, what is the amount invested at each rate? Well, I know I total 370, so that's what this is going to equal when I'm all done. Now, I have a 5% account. 5% is what is a decimal? 0.05. Do we know how much we're investing in this 5% account? No, we don't know how much we're investing. We know total we're going to invest $6,000. X, that's where our variable comes. Plus we're going to invest in an 8.5% account. So 0.0, how do I write 8.5% as a decimal? 0.085. Now the question is, how much do I have invested in that account? And I don't want to introduce a new variable. I need to stick with one variable. Well, if I have a total of $6,000 available, and I've already used up X, how do you find what's left over? 6,000 minus X. We have a total of 6,000, and we have already used up X dollars. I don't know how much that is, but what is left over is 6,000 minus X. There's our equation, and we are going to see several other mixture problems that are set up very similar to this. You can help me with your calculator. 0.05x plus, I need to distribute here. What's 0.085 times 6,000? 510 minus 0.085x must equal my 370. So if we put our x terms together, what do we get?
Negative 0.035.
0.035 x plus 510. So we will subtract our 510 next.
Negative 1.
And then we can divide by our negative 0.035. 4,000? Now the 4,000 was $4,000 in the 5% account, because that's where we made our variable. The 5% account was the X. How much do we have left over? 2,000. 6,000 minus 4,000. We have $2,000 left over in the 8.5% account. When you are doing application problems, you have made up the variables. So saying X equals or Y equals is meaningless. You need to identify what have we just found. Here we found how much was in each account, so we need to say. And I need to come back here and identify, it's 610 shoes. We need to say what we have found when we've done it. This one, not going to take much time on this. This happens to be the QBR, quarterback rating. And if you have ever wondered what the formula was, you football fans, there it is. All this is about is they have given us a formula. They have explained what each variable stands for. C, percentage of pass completions. Y, average number of yards gained. They explained what all the variables are. Then they tell us, hey, here's a person called Philip Rivers, and he happened to have these numbers. So you substitute the numbers into it. And when you are done, you figure out that in whatever season this was, Philip Rivers had 105.5 QBR, quarterback rating. You'll get some where you're just given the formula and you fill in the values. Won't spend more time on that. Rate problem. There are different types of rate problems. A runner runs a course at a constant speed of 6 miles an hour. 1 hour after the runner begins, a cyclist starts. Same course. They go at a constant speed of 15 miles an hour. How long after the runner starts does the cyclist overtake the runner? Well, this is a rate times time equals distance. Now you need to be familiar with that, just like you need to be familiar with perimeter is 2 lengths plus 2 widths. Rate times time equals distance. So I have a runner and a cyclist. Can you tell me how far the runner goes compared to how far the cyclist goes? Read that problem carefully and compare. I don't know if it's 20 miles. That's not my question. Is one farther than the other? Are they equal to each other in the distance they have gone? It's going to be critical to us in figuring out how to set this problem up.
The runner is ahead by 1 hour.
The runner in time has started an hour before, so the time is not the same. But how about the distance? What does that mean? Okay, or caught up to them. Can you compare the distance of how far the runner has gone compared to how far the cyclist has gone when that happens? The same. That's what's key on this one. The runner starts an hour before. It's been an hour and they're running here. Then the cyclist starts, but at some point, because the cyclist is faster, they have gone the same distance. They meet each other. That is going to be the key here. The distance of the runner at some point equals the distance of the cyclist. Now, how do I get distance? I get distance by rate times time. Rate of the runner times time of the runner is going to equal rate of the cyclist, time of the cyclist. Now, Johnny, you mentioned 1 hour after the runner begins, the cyclist begins. I want you to tell me, how does the time of the runner compare to the time of the cyclist? Now, I'm not just saying Johnny has to tell me, but you as a class. Read that, and you come up with the comparison in the times between the two. There it is. The runner has gone an hour more than the cyclist because they left an hour before.
That means 6 miles a day.
So the time of the runner is the cyclist plus 1. Now we're not trying to solve it yet. We're not trying to solve it yet. We're just trying to figure out what is the time. And the runner's time is the cyclist plus 1. That is going to be where I substitute right back here. The rate of the runner times the time of the runner. Well, the time of the runner is the cyclist plus 1. Time of the cyclist plus 1. Rate of cyclist, time of cyclist. Now they've told me the rates, so I can put numbers there. The rate of the runner is 6. The rate of the cyclist is 15. And now the only thing I don't know is one variable, the time of the cyclist. That's what we have to do if I'm going to solve, is get it down to one variable. We've managed to do that, so we should be able to solve this. I'm just going to call it t for, well, I better stick with t, Susie. I'm just distributing here. 6 times 1 is called 6, not 61. So I'm going to subtract my 6. 6 equals 9. And then if you wouldn't mind dividing for me, how long was the cyclist gone? You can even give it to me as a reduced fraction if you want. It's what? Yeah, divide by 9 once you reduce 6 over 9 for me. 2/3. 2/3 what? Hours. This is the time of the cyclist. And it's measured in miles per hour. It's hours. 2/3 of an hour. How long after the runner starts does the cyclist overtake the runner? The cyclist is going to overtake the runner 2/3 of an hour after the runner starts.
Yeah.
How long after the runner starts? So I answered the question, how long was the cyclist? So how long is the runner? I better add an hour to that. 2/3 plus 1. So the runner is 1 2/3 of an hour. So we better go back and make sure we read the question correctly. The last one was a rate problem. It was a rate times time equals a distance. But there are many kinds of rate problems. Rate times time will always equal some total. If my rate is in miles per hour, well, the total is going to be miles, my distance. If my rate is in dollars per hour, it's going to have a total of dollars when I am done. So that last problem and this problem are the same kind of problem. It also is a rate problem. Pump A can fill a pool in 6 hours. Now let me just show you how that is a rate. This is the rate of pump A, 1 pool in every 6 hours. 1 pool every 6 hours. Now if I multiplied this times time, I would end up with what when I'm done? Pools. So this is a rate problem that when I am done is going to have a total of the number of pools. Pump B can fill the same pool in 3 hours. the rate of pump B is 1 pool every 3 hours. How long will it take for them to fill the pool if they both are used at the same time? So we want to fill a total of how many pools? 1. So I am just going to have rate times time, rate A, time A is running, plus the rate of pump B, and the time pump B is running. And when I'm done, I want to have 1 pool filled. Now let's think about the times. Can you tell me the time comparison between how long pump A and how long pump B is running? So this is good reading comprehension. This is what we're doing today with a math twist to it. Can you figure out the comparison between the two? You have to think of the story. Think of it as a story. How long does pump A run compared to pump B?
Twice as slow.
Now careful, that's the rate. You're answering a rate question for me.
So what do you want to know?
I want to know the time comparison. Now I don't know how long, but I just want to know. That's the rate again. You're telling me a rate again.
So, like,
Here's my pool. You see my pool? I put pump A in, I put pump B on, I flip the switch, and I fill a pool.
Pump B will finish 3 hours faster. That's great.
How long are pump A and pump B running compared to each other? Same. I've got 2 pumps in the pool. I turn them both on, and I wait until the pool fills. They are running at the same time. They both are pumping at the same time. How long will it take to fill the pool if both pumps are used? I just have both of them running.
In 1 pool?
1 pool. 1 pool. Same pool. 1 pool. So let's then say, oh, that's just time. The time is the same. So now I have 1/6 T plus 1/3 T, and when I'm done, I get 1 pool. Well, these are already like terms. Now I might need a common denominator of 6, so that's 2/6. So what do you get when you add those together? 3/6, or 1/2 T equals 1. How do you get rid of that 1/2? Multiply by the reciprocal, which will give me 2. 2 what? What did we just find? Hours. 2 hours. That's how long it's going to take you to fill that 1 pool, both pumps running. So this one is also simply a rate problem, where rate times time equals something. Now let me back up here. This was a rate problem. We had to figure out that their distances were the same here. Here we had to figure out that, hey, they both are doing a task together, and when they're done, we know what the total is. The total is 1 pool. So let's look at another example. This is another mixture problem. Now this one is going to be like, there it is. It's going to be like this one. They're the same kind of problems. The words are different, what they're talking about is different, but the math is the same. A chemist mixes 11% hydrochloric acid with a 6% hydrochloric acid solution. What's the symbol for hydrochloric acid? HCl, very good. How many milliliters of each solution should the chemist use in order to make 600 milliliters of a solution? So that's what I want to end up with. That happens to be 8% hydrochloric acid. Well, let's start. Our mixture, we have an 11%. Just like earlier, we had a 5% investment. Now it's just 11% chemicals. The math is the same. Do we know how much we have of this solution? The 11% solution.
No.
X. We're going to add to it a 6% solution, 0.06. There's a clue. How much do I have of that? Can you read the problem and tell me how much I have left over? Notice I have a total of 600 milliliters when I'm done. I mix 2 things together and I have a total of 600. So if one is X, how much is there for the other one? 600 minus x. 600 minus x. Remember back here, I had a total of $6,000 invested. If x is the amount for 1, then what's left over? 6,000 minus x. Exactly the same kind of problem. Now, when I'm done, I get a total, and it happens to be an 8% solution. Okay? 0.08 times the amount that I have. Here's x, here's x. What's the total amount that I have? It's not hard, don't make it hard. 600. 600. There's our equation. It's a mixture problem just like before. We need to distribute there, so again, if you could help me. 0.06 times 600.
36.
Exactly.
Yes.
Minus 0.06x equals
48.
48. So if I get my like terms together, well, 11 minus 6 is 5, so I can even do that. 0.05x plus 36 equals 48. Subtract our 36. Divide by 0.05. 240? Now, 240 milliliters of, where did our x? The 11%. So how much is the 6%? Yeah, take 600 and subtract the 240, 360. There must be 360 milliliters of the 6% in order to give us what we want. And we have seen 2 rate problems and 2 mixture problems. So our very last one, I wonder what it is. A mixture problem. Thankfully, it's not a mix of both. That'd be a good one. No, it's not. How many ounces of pure silver costing $10.50 an ounce must be mixed with 60 ounces of a silver alloy? It costs $7.35 an ounce. We're going to produce, or we're going to end up with, a silver alloy that happens to cost $9 an ounce. Okay, well, we have this first thing that's 1050, 10.5. How many ounces do we have of this 1050 stuff? X, we don't know. We're going to add to it 60 ounces, and it's $7.35 an ounce. Well, $7.35, and how much do I have of it? 60. They actually told us 60. When I'm done, I want to end up with something that costs $7.35. And how much do I have when I'm, oh, wait a minute. 9. I already used my $7.35. 9. And how much do I have when I'm done? This might even help you down here. X plus 60. I have X amount of this, I have 60 ounces of this, so when I add them together, I have X plus 60 ounces when I'm done. There's our equation. So I'm not going to take the time to solve this one. They have it right up here. You can see the same equation right there, and they figured it out, whatever their answer was.